Now let's do an example with root mean square velocity of gas particles. You may recall from the previous lecture that the root mean square velocity is calculated as the square root of 3 times RT over big M. And we just want to remember for root mean square velocity calculations that the R that we want to use is 8.314 joules per mole Kelvin. Temperature, we want always in Kelvin so that the units match. And M is like the molecular weight, but we want it to be in kilograms per mole, the molecular weight of whatever the gas particle you're talking about in kilograms per mole, because joule is kilogram meter squared per second squared. Taking the square root then will give us units of meter per second for the root mean square velocity. So let's apply this to this question. What is the average velocity of nitrogen gas at 25 degrees Celsius? What is the average velocity of nitrogen gas at 1,000 degrees Celsius? So let's plug numbers into this equation for root mean square velocity. Root mean square velocity at 25 degrees Celsius is going to be 3 times 8.314 joules per mole Kelvin times the temperature in Kelvin. Now 25 plus 273 is 298 Kelvin. And we are going to put that over the molecular weight of nitrogen in kilograms per mole. Now nitrogen has a molecular weight of 28 grams per mole. So if I want that in kilograms, I am going to have to divide it by 1,000, because 1 kilogram has 1,000 grams. So this is going to be equal to 0.028 kilograms per mole. Okay, so I'm going to put that in my denominator, 0.028 kilograms per mole. You have to have kilograms because, again, a joule is a kilogram meter squared per second squared. So having the kilograms enables me to cancel the units properly. This gives me 515. Now, the units would be meters squared per second squared under the square root, but when I take the square root, that just gives me meters per second. So 515 meters per second is the root mean square velocity of nitrogen at 25 degrees Celsius. Now I could do an exactly similar calculation at 1,000 degrees Celsius. Everything is the same except the temperature. So I still have my R, 8.314 joules per mole Kelvin. But now I have 273 plus 1,000, so that's 1,273 Kelvin over the same molecular weight, 0.028 kilograms per mole. So do all of that arithmetic and then take the square root, and you get a root mean square velocity of 1,065 meters per second. So notice the difference between these two answers. It is a whole lot faster at 1,000 degrees Celsius than it was at 25 degrees Celsius. So doing this calculation shows you how much velocity of gas particles depends on temperature. The higher the temperature, the faster the average velocity, for sure. But I really want you to remember that what we're calculating here, this is root mean square velocity. It's a mean. These are average velocities of gas particles. So what this means graphically is if I were going to plot the number of molecules, the number of gas particles, as a function of their root mean square velocity, I would see a broad range. So you would have kind of a range of velocities. Here's an example of, let's say, the red line is going to be at 25 degrees Celsius. So that would put the root mean square velocity wherever I calculated it. I think it was 515 meters per second. The one at 1,000 degrees Celsius is going to have a much broader distribution. So that's going to maybe look something like this. That's a little ugly the way I drew it. Let me try to do that again with a more defined peak. There we go. Broader distribution, maybe a lower peak. And the average velocity there would be around 1,000. What did I calculate? 1,065 meters per second. So the green line would be the distribution of velocities at 1,000 degrees Celsius. So this kind of graphically shows what the velocities of the nitrogen gas molecules would be at the two different temperatures. So I want to emphasize again, gas particles have this whole broad range or distribution of velocities. And oops, I don't know why that erased my 2. That's at 25 degrees Celsius. So the higher temperature, the 1,000 degrees Celsius, just meant that we have greater average velocity, which is kind of around the middle of that range. However, I could have a very slow particle, I could have a very fast particle at either temperature. Okay, I could have a particle falling somewhere here, even at 25 degrees Celsius. I'd be less likely to, but I could have a pretty fast particle there too. But the average velocity is going to be lower at lower temperatures. Another important concept to think about with gas kinetics is the mean free path. Mean free path. I want to define what that is because it sounds pretty technical, but it really isn't. So if you imagine you're a gas particle in a sample, continuous random motion, any given gas particle is going to be changing its course constantly as it hits other gas particles and as it collides with the walls of the container, right? So you can imagine you're moving until you hit something, then you bounce off and change course. So the mean free path is the average distance that a gas particle travels between collisions. Okay, that's all the mean free path is. It's basically the distance that it travels before it bangs into something. Okay, so when you see a description of the mean free path, that's all it is, the distance that a particle travels before it hits into something. The mean free path is very small. Okay, for example, for oxygen at standard temperature and pressure, the mean free path is 1 times 10 to the minus 7 meters. So the mean free path is very, very small. Particles don't travel very far before they bang into something else. All right, another concept under the umbrella of root mean square velocity is these two phenomena, diffusion and effusion or effusion. I want to define what diffusion and effusion are. You probably have heard of diffusion. It's just the mixing of gases. So for example, if you open a bottle of perfume, the volatile organic compounds in that perfume will come out and slowly they'll diffuse through the air. Okay, so eventually on the other side of the room, you'll be able to smell them. So everybody should be kind of at least familiar with the concept of diffusion. Effusion is a little more technical. Effusion involves a special apparatus where we are passing gas. Okay, I'm 12, but that's funny. We're passing gas through a small orifice in an evacuated chamber, so a chamber under vacuum. The rate of effusion is what's generally measured in effusion experiments. And the rate of effusion is defined as the speed at which the gas moves into the chamber. So when we do diffusion or effusion problems, the mathematical relationship that's useful is Graham's law. And Graham's law takes the rate of effusion for whatever the first gas is. I'm going to call it gas 1. And you just take the ratio of that with the rate of effusion of a second gas. So that's what's generally done. You compare the rates of effusion of two gases. And what you find is that the rate of effusion is inversely proportional to the molecular weight. So I'm going to say inversely proportional. That means that the molecular weight of gas 2 is going to be on the top, and the molecular weight of gas 1 is going to be on the bottom. And the reason I put the square roots in there is because Graham's law really comes from the root mean square velocity. So if we take the root mean square velocity for gas 1 and we put it over the root mean square velocity for gas 2, and we plug it into the whole equation there, I'm going to have 3RT over M1 divided by square root of 3RT over M2. So the 3RTs, the square root of 3RTs are going to cancel, and I'm left with the square root of the molecular weights, or I'm left with the square root of the reciprocal of the molecular weights. So this simplifies down to this expression that I gave you for Graham's law. And you can calculate the diffusion rate in the same way. So you can also call this the rate of diffusion instead of effusion. So I should make that note that you can use for diffusion too, the same relationship. So what this means, again, is that the rate of effusion or diffusion of a gas is going to be inversely proportional to the square root of the mass of its particles. The heavier the gas, the slower it goes. The lighter the gas, the faster it goes. Okay, so that should make sense intuitively that a heavier gas will travel slower and a lighter gas will travel faster. Okay, that's all this equation is saying. So let's put it into action in a problem. The distance traveled by oxygen in a tube is 0.48 meters in 10 seconds. A second compound, which we know is either dinitrogen monoxide or nitrogen dioxide, travels 0.40 meters in 10 seconds. So using that information, can we tell which gas it is? So we can use this Graham's law. We don't need to have necessarily the rates. We can also just plug in the distance because we have the both of these are 10 seconds. You can use the rate if you want to, but well, okay, I don't want to confuse you guys. So let's just put the rate of the gas 1. So the rate of gas 1, or let's say the rate of O2, over the rate of the mystery compound. I'm going to call the mystery compound MYS for mystery. The rate of the first one is 0.48 meters per 10 seconds. Okay, rate is in meters per second. And that's the rate of the oxygen. And the rate of the mystery compound is 0.40 meters in 10 seconds. So you see, I can cancel out the 10 seconds there. And that is going to be equal to the square root of the molecular weight of the mystery compound over the square root of the molecular weight of oxygen. Remember that with this Graham's law thing, I have this kind of cross here where it's an inverse relationship, if that makes sense. So I know the molecular weight of oxygen. I'm just going to leave it in grams per mole because it's a proportion. So I don't need to convert it. So I'm going to have the square root of the molecular weight of the mystery gas over the square root of the molecular weight of oxygen, which is 32 grams per mole. So if I simplify everything and then square it to solve for the molecular weight of the mystery gas, I find that the molecular weight of the mystery gas is 46 grams per mole. So I suggest you pause and make sure you can go through and get that answer by doing the simplification here. So which compound does that match? Well, you can calculate the molecular weight of both of these. And it looks to me like 46 grams per mole is going to be NO2. So that is the mystery gas, nitrogen dioxide in this case.